imaginary direction. So we'll be -1, -2, -3. The point where those two come together, this here could represent a vector representing this complex number. We have 3 units in the negative imaginary direction and 2 units in the positive real direction. And so this is the number 2, -3i. So again, you can see that the pictorial representation gives kind of a good idea of what these complex numbers look like. So hopefully that helps us understand what complex numbers are. And that's how we show. That's why much fun, right? Well, also as I'm saying that, I have like different ways. Welcome to my lecture online. For the request of some of the viewers, we're going to do a series of complex numbers and complex functions. The first you may say, well, is that really all that complicated? And it turns out it can get quite complicated, so therefore we're going to do a series, we're going to do a set of videos on complex numbers and complex functions. So first I want to define what a complex number really is. And it's not as tangible as you would like it to be. For example, when we look at the number line, we can place a number on the number line and it represents a real thing. For example, you can have the number 2 or the number 3, and that can represent apples, or that can represent miles or meters, or volume, represent gallons. We have real tangible things that we can attach to real numbers. So the imaginary numbers don't fall into that category. And if we draw something on what we call an imaginary versus real plane, so we have on the horizontal axis the real number line, and on the vertical axis the imaginary plane, notice if we get off the number line, for example, this one right there, that point represents an imaginary number. It has a real part, the number 3, but it has an imaginary part, the number 2i, because it's 2 units away from the real axis. That still doesn't tell us what it really is. But what we understand now is that an imaginary number has a real part belonging to the real number line, and it has an imaginary part belonging to the imaginary plane away from the real number line. The best way to really define what a complex number is, it's simply a mathematical tool that has some really good reasons for being. There's some really good applications that we'll get into in just a moment. But yes, imaginary numbers are actually very useful things. First of all, we have to realize that there's an I associated with the imaginary part. And I has a very real definition. I is defined as the square root of -1. So if I is the square root of -1, that means if we multiply I times I, or if we square I, we should get what's underneath grammatical. And indeed, if we go I times I, which is I squared, we get -1. What happens if we get I cubed? Well, I cubed is I times I times I, which means it's I times I squared, and I squared is defined as -1, so this becomes -I. And then if we multiply I times I times I times I, which is really I to the 4th power, which is I squared times I squared, which means -1 times -1, we get a +1. So when we work with the number I, and indeed this is a number, it's an imaginary number, we can work with it. When we multiply an imaginary number by itself, we might get a real number again. So there are some relationships there that we'll get into a little bit more later. To get a better feel and sense for what an imaginary number is, besides just simply claiming it as a mathematical tool, we can see there's some very real applications. For example, if we have a quadratic equation, y equals x squared plus 4, and they're asking you to find the roots, the first inclination would be, well, it doesn't have any roots, because the graph is across the x-axis. This is our x-axis here, this is our y-axis there, but it doesn't have imaginary roots. If we flip over the parabola, then we can see that that image, when we flip it over, does cross the x-axis, and those are then the 2 imaginary roots. And using the quadratic formula, we can indeed find what those roots are. We can also use imaginary numbers in electric circuits. For example, here we have a circuit with a time-varying voltage source, an inductor, and a resistor. We can then draw what we call here a phasor diagram that shows us the voltage across the resistor and the voltage across the inductor, but notice they're 90 degrees out of phase. They don't happen at the same time. So the voltage across the resistor and the voltage across the inductor can be thought of as imaginary numbers. They have a real part and an imaginary part to it. If we project those voltages then onto the horizontal axis and only take the real parts and then add them together, we then get the total voltage across the circuit, and that will always be the same quantity driven by the voltage of the source, but independently, the voltage of the resistor and the voltage across the inductor, if we measure them independently, could add up to more than the voltage of the source because they're out of phase. And so imaginary numbers help us out there. We can use imaginary numbers in Fourier transforms. If we have an electrical pulse in the time domain, and then we transform it via the Fourier transform into the frequency domain, we can see that the equation necessary to do that requires the imaginary number in the exponent there underneath the integral sign. So again, it shows that, well, we need it, otherwise we couldn't do that Fourier transform. And what's also interesting is, another application, Euler formula shows that we can have e to the ix, again this is an imaginary number as the exponent of the constant e, can then be expressed as the sum of the cosine of x plus I times the sine of x. So we have a relationship between trigonometric functions and exponential functions here through that imaginary number I. And there's many more applications that exist using the number I or using the imaginary part of a complex number. So it's not just that it's a fancy word, it's not just that it's an interesting concept, it's actually a very useful tool in mathematics. So there's a good reason for us to learn how to use it and to work with it. And that's the intent of the videos to come, is to show all the various applications and also we'll show you how to find the derivative and the integral of exponential functions as well at the end. And that's why we're doing a series on complex numbers. Welcome to our lecture online. Sometimes you're faced with an infinite sum like this, and you wonder, how do you tell that it converges or diverges? So that's the question. Does it converge or does it diverge? Well, what you can see is that it looks very similar to something like this. So it is similar to the following. It's a sum of n equals 1 to infinity of 3n to the 4th divided by n to the 5th. And we drop out the other two terms in the numerator and the other two terms in the denominator. You may say, well, why do I do that? Aren't they important? Well, it turns out as n becomes large, and it will become large quickly, n to the 5th and n to the 4th will far overpower the value that n to the 3rd and n to the 2nd will get, and especially 2 and 5 to the n. So they become insignificant very quickly, so only this drives the infinite series as n becomes large, and so therefore this will determine whether or not it converges or not. So when we look at that, we can say, well, this is equal to the infinite sum of n equals 1 to infinity of 3 times n to the 4th divided by n to the 5th, which is 1 over n. And now we have an infinite series of 3 times the sum from n equals 1 to infinity of 1 over n, which is equal to 3 times 1 over 1 plus 1 over 2 plus 1 over 3 plus and so forth. And we know that that series does not converge, so if that doesn't converge, adding those small sums at the end will not make any difference. It will not converge anyway, so therefore we can say that this series will diverge. Again, using the comparison test is often a very good way from trying to do something very difficult to turn it into something that's rather simple. And that's how it's done. Welcome to our lecture online.
Homepage 自分で作ってみませんか？こいつなら素敵なホームページを簡単に作成できます。個人ビジネスからアーティストまで豊富なテンプレートをご用意しました。デザインは自由自在、ドラッグ&ドロップの簡単操作で思い通りにアレンジできます。実績を編集し、ホームページにぴったりな背景を選んだ後は、ギャラリーを追加して写真を公開しましょう。ネットショップだってとっても簡単にオープンできます。ほんの数クリックだけで SNS との連携も完了。その他にも Google マップやお問い合わせフォームなど100種類以上の機能を自由に追加できます。あとはオンラインで公開するだけ。スマートフォン対応の素敵なホームページの完成です。さあ、あなただけのホームページを無料で作成しましょう。
Next, we want to find the moment of inertia of a triangle. And then we realize that the triangle can be positioned in two different ways. We can have a triangle like this, and then we try to find the moment of inertia relative to the x-axis, and of course we realize that most of the area, as it would be if you had an object with mass, most of the mass is close to the axis of rotation, so therefore we expect a smaller moment of inertia relative to the x-axis. We could also have the triangle situated like this, with most of this area, or most of its mass, far away from the x-axis. So even though these triangles have the exact same area, just have them situated differently, you realize you're going to end up with a different moment of inertia. The moment of inertia of this one relative to the x-axis is expected to be larger. The question is, how much larger? What are the moments of inertia? Well, we're going to start with the top triangle first, and then the next video we'll do the bottom triangle to see how they differ. So we're going to find the moment of inertia of this triangle. Here we have a small area element called dA. We have the width x and the height dy. The equation here is the equation y equals nx plus d from algebra. But the slope in this case is going to be a minus slope of negative y overrun from minus h over b times x plus d y intercept of h. We're going to need that equation solved in terms of x, so that it's right here, x is equal to b minus b over h times y. So now we're ready to find the moment of inertia relative to the x-axis. So I sub x is equal to the integral. We're going to integrate over all these little area elements from y equals 0, so y equals h, 0 to h, of the distance squared, that would be y squared, times the area element of dA. Taking in what dA is equal to, this becomes equal to the integral from 0 to h of y squared, and dA is going to be x times dy. Here's where we're going to need to find the value of x in terms of y, because we have a differential of dy, so we're going to plug in that value right there. So this is equal to the integral 0 to h of y squared times what x is equal to in terms of y, which is d minus d over h times y times dy. And now we realize we're going to end up with two different integrals, so let's separate them. This is equal to the first integral. We'll have the constant b, taking out the integral sign. We have 0 to h for the limits, and then we have y squared dy, that's the first integral, minus the constant of b over h, times the integral also from 0 to h, and now we have the y times the y squared, that's y cubed, times dy. So those integrals can be readily integrated. So this becomes equal to, the first one becomes b times y cubed over 3 evaluated from 0 to h. And the second one becomes minus b over h times y to the fourth over 4 evaluated from 0 to h. Of course, when we plug in the lower limits, we get 0. When we plug in the upper limits, we get the following. The first one, we get 1/3 b times h cubed minus, and notice that action would be the moment of inertia if this action would be in a rectangle of width d and height h. So we subtract from that this quantity right here, which is 1/4 b over h times h to the 4th power. You can see that this h will cancel off one of those, so this ends up being 1/3 bh cubed minus 1/4 bh cubed. Common denominator would be 12. That gives us 4. So this is equal to 4 over 12 bh cubed minus 3 over 12 bh cubed, which is equal to 1/12 bh cubed. But now let's solve it in terms of the area of that rectangle, or triangle, I should say, not rectangle, triangle. So this is equal to, and we know that the area of that triangle would be 1/2 the base times the height, so it would be 1/6 times 1/2 base times the height, and then we have left an h squared. And so this becomes equal to 1/6 the area of the triangle times h squared. And that would be the moment of inertia of that triangle situated with the base against the x-axis and finding the moment of inertia relative to the x-axis. So it's 1/6 the area times h squared. Well, let's write that down up here. We have 1/6 the area times h squared as being the moment of inertia relative to the x-axis for the triangle situated like that. Now we'll do this again on the next video, the second example where we have now turned the triangle upside down to see what we get this time. And that's how it's done. Sometimes we end up with an infinite sum that looks very similar to one that we can easily find the conversions or diversions of, and we can find the sum of. It seems really that this can be written to be smaller than the infinite sum for n equals 1 to infinity of 1/3 to the n power. That's because the denominator here is larger than the denominator here, so for every denominator in the series, the denominator here will be larger than the denominator there, which means the fraction will be smaller in this case, which means the lifetime is indeed smaller than the lifetime. Now, does that converge? Well, we can make that look like a geometric series, and let's go ahead and try to do that. So this can be written as the infinite sum of n equals 1 to infinity of the quantity 1/3 raised to the n power. That's exactly the same thing, because 1 to the n power, no matter what n becomes, is always equal to 1. Which means we can then factor out a 1/3, so this can then be written as 1/3, or I should still say the sum, n equals 1 to infinity, of 1/3 times 1/3 to the n minus 1 power, and now we have a geometric series. Because now we can say that the ratio is equal to 1/3, and the constant a is also equal to 1/3. And we can find the sum of that geometric series. So the sum is equal to a divided by 1 minus r, which is 1/3 divided by 1 minus a third, which is 1/3 divided by 2/3, which is equal to 1/2. So we know that this series converges to 1/2, which means this converges to 1/2. And since we know that the left side is left of the series here, since this equals 1/2, we know that this must be equal to 1/2. So the sum of n equals 1 to infinity of 1 divided by 3 to the n plus 5 must be less than 1/2. So therefore, we know that it converges. So we know this goes. Therefore, the series converges, and we know that the sum must be less than 1/2. So using a differential test, this is something you're familiar with. Why not help yourself one you're not familiar with? And that's how it's done. Welcome to my lecture line. In this video, we're going to find the moment of inertia of a hollow circle relative to the center mass of the circle. So we're trying to find out what the moment of inertia would be as it's circling in that direction. So we have an inner radius r1 and an outer radius r2. We have a small area element dA, a distance small r away from the center with a thickness of dr. So the area dA is equal to the circumference 2 pi small r times dr. Also for reference, the area of the hollow circle would be equal to the area of the outside radius minus the area of the hollow part taken out. So how do we find the moment of inertia relative to the origin? Well, to do that, we simply use the integral. We say that moment of inertia is equal to the integral of the distance to the area element squared times the area element. And we'll integrate that from the inner radius to the outer radius, so from r1 to r2. So dA is equal to 2 pi r dr, which is the integral of r squared times 2 pi r dr. From r1 to r2, and we can take the 2 pi out. So this is 2 pi times the integral from r1 to r2 of r2 dr. So now we're ready to integrate that. That's relatively easy. It becomes equal to 2 pi times r to the 4th divided by 4, evaluated from r1 to r2. Notice I can take the 1 over 4 out. 2 divided by 4 is 1 over 2. So this becomes equal to pi divided by 2 times, when I'm putting the upper limit, I get r2 to the 4th power minus, when I'm putting the lower limit, I get to the 4th power. So that's the moment of inertia of a hollow circle. But let's take it one step further. Let's go ahead and factor what we have there. So that means that this becomes equal to pi divided by 2 times, and we have the difference of two quantities raised to the 4th power. So this can be written as r2 squared minus r1 squared multiplied times r2 squared plus r1 squared. And then we realize over here that pi times r2 squared minus r1 squared is actually the area of that hollow sphere, or that hollow circle. It's not a sphere, it's a circle. So pi times this is really the area of that circle. So what we can then do is we can go ahead and factor it out. So we have 1/2 times, like this, pi times r2 squared minus r1 squared, and then multiply it times r2 squared plus r1 squared. Now recognize that this here is simply the area of that hollow circle. And we can write this as 1/2 times the area of the hollow circle times r2 squared plus r1 squared. And this then becomes the moment of inertia of a hollow circle. Instead of using the mass, if we had an object with mass, that would become 1/2 m r2 squared plus r1 squared, or if you want to first order, it doesn't matter. So in this case, instead of having m, we're going to have area. The area of the hollow circle is 1/2 times the area times r2 squared plus r1 squared. And that's the moment of inertia of the hollow circle rotating about its center of mass. And that's how it's done. Separately. So how do we do that? Well, we can say that 2 is going to be equal to, when we multiply a times n minus 1, plus when we multiply b times minus 1. I should say b times n plus 1. What we're actually doing here is we're writing this over a common denominator of n plus 1 times n minus 1, which means that a times n minus 1 plus b times n plus 1 has to equal the numerator of that. Now we can solve this for a and b. So this, if we write this out, we say that 2 is equal to a times n minus a plus b times n plus b. And from that we can conclude that a plus b must equal 0 because there's no n counterpart on the left side of the equal sign, and we can say that minus a plus b is equal to 2. So that means that b is equal to minus a, and if I plug that in here, we have minus a is equal to 2, or minus 2a is equal to 2, or a is equal to minus 1. Write that right, minus 1 there. Which means that this is now written as the infinite sum of a, which is minus 1 over n plus 1, plus b, which is 1 over n minus 1. Alright, so now we're going to sum those up separately.